So, welcome back to another beautiful presentation on our control system subject. Today, I am going to explain you about the impulse function. If the input signal is impulse function, then what is the Laplace transformation of it? And then afterwards, we will see the first order control system. Okay, first order control system, and what is the response of that system, because the first order is the very basic building block of any control system in order to study the response of the given control system. As we are studying the time response analysis of the control system, basically, so it starts from the first order system and then we will move for the second order system, like that. So right now let us see. By the way, this is our lecture number 25, in which let us see the impulse function. So far we have covered, since if you go back our previous presentations, in presentation number 23 or lecture number 23, we have discussed about unit step signal, and then we have seen the next one, ramp signals also, and parabolic signal we have subsequently seen in our previous presentation, that is presentation number 24. In today's lecture, that is lecture number 25, we see the impulse signal. Impulse signal. It is impulse signal. This is another important type of input signal. Sometimes we can apply unit step signal and then ramp signal and parabolic signal, and this is the another type of important signal that can be applied as input to the any control system. That is what impulse signal. What is impulse? Impulse is defined as impulse has infinite magnitude at time t equal to 0, and it has 0 value at all other values of time. That is the definition of impulse signal. Mathematically, the impulse signal can be defined as, and however, this can be represented by the letter delta of t. Remember that. So impulse signal can be denoted by delta of t, like that. This is the representation of the impulse signal, and mathematically this can be defined as delta of t. Delta of t is equal to, you can say, infinite at t equal to 0, and it is 0 for all values of t is not equal to 0. This is the mathematical definition of delta of t. Impulse function or impulse signal. It means that at t equal to 0, it has infinite magnitude. It has very infinite magnitude at a time t equal to 0. And all other values of 0, you can take either plus 1, plus 2, plus 3, plus 4, and if you go to up to plus infinity, or otherwise if you take minus 1, minus 2, minus 3, minus 4, and up to you go to minus infinite, for all these values the value is 0. But at t equal to 0 itself only, it has infinite magnitude. So graphically this can be represented as, like this. Graphically this can be represented as like this. This is time, axis. This is 0. In fact, this is 1, 2, 3, 4, 5, and so on. So you can go up to plus infinity. You can go plus infinite. Then it is minus 1, minus 2, and then it is minus 3, minus 4. Go up to minus infinite in this way. At t equal to 0, it has little bit thicker line you represent. Arrow mark can show like this. Okay, this is what actually. Okay, so your signal will be available here only. I can show with red, otherwise this is. Likewise, for all other values you can draw line this. This is the graphical representation of your impulse signal. Means at t equal to, this is what your t equal to 0. At t equal to 0 you have, this is what your delta of t. Delta of t has infinity, the magnitude is infinite. Whereas for t is equal to 1, t equal to 2, for all these values, that delta of t is 0. That is what impulse signals definition. Okay. So for any given control system, if the input is, if your R of t is input, no, so if your R of t is your impulse signal, then the response of the system is called as impulse response. The response means the output of the system is called as impulse response. Okay. This is what about the impulse signal and its Laplace transformation. And one more, the very important property, and one more important note that I would like to bring to your information is that, so the in another way, this the impulse signal can also be defined like this. The impulse signal has the infinite value at t equal to 0, and which is available for a short duration only. For short duration only. So for a very short duration, it has infinite value. That is the meaning of it. Okay, for the short duration of time, very short duration. That's why practically it is very impossible to have impulse signal. Actually, practically it is not at all possible. That's why we will imagine that for a short period, even that is less than 1 seconds, always the time duration is less than seconds only, maybe milliseconds, like that. For short period of the time, it has the magnitude, the very high value of magnitude it has. That's what the important property of this impulse signal. And one more important property is that if we represent graphically, so short period means it is 0 basically, it is 1 and it is 2, it is 3 and so on and so forth, -1, -2, like that. So here, let us say for example, somewhere for convenience I am less than 1 only, or obviously for our convenience let us take 1 as t as 1. This is time axis and this is what your delta of t basically. Consider t is equal to 1 at least to understand the duration of the pulse impulse. Likewise, so for t is equal to 1, it has the magnitude, let us say a, for example. So for the short period of time, the magnitude has higher magnitude, but however I am representing a, some value we should consider. Okay, some value we should consider. Practically, ideally it is 0. Remember that the ideally the time is 0, and for time equal to 0 the magnitude is infinite. Those are the ideal values of your impulse signal. So practically we will consider some value. So let us consider as t is equal to 1 second and some magnitude is a. Then from this you can say this goes up to minus infinity, and then this is up to minus infinity, that is plus infinity time. So the very important property is that, so the area under the curve, this is what the curve, if you say, this is the area available for the impulse signal. This is called area. The dotted shaded portion, this is called the area. So the area under the curve, this is what the curve basically, that shows like this, minus infinity to plus infinity. It is delta of t dt is equal to 1. This is very important property of your impulse signal. So the area under the curve of a unit impulse signal, unit means again your magnitude value becomes a, remember always. So unit impulse, so unit impulse signal, so for unit impulse signal your a becomes 1, your a becomes 1. Therefore this is one of the famous important property. The area under the curve is equal to 1. That's why from this property you can directly say that the Laplace transformation of your impulse function, impulse signal, otherwise delta of t, is equal to it is called as 1. From that property, only the Laplace transformation can be directly given as the Laplace transformation of your delta of t is equal to 1. The value is 1. Is it not? The value is 1. So this is what the Laplace transformation of the impulse signal. And obviously the next type of input signal is sinusoidal signal. For the in general, most of the time we will use the step input, and in a very rare occasion ramp and parabolic and impulse will be used. Sinusoidal is very rare occasionally we will use basically. So the most of the time we will use these four only, but for a namesake, and we have mentioned that sinusoidal, but in the very important input signal is unit step only. That is the very reference and very basic initial input signal that we normally consider to study the behavior of the control system. Unit step and unit ramp, unit parabolic and impulse signal. These are the very important thing. Okay, these are the various input signals that are to be applied to a control system. Okay, now sinusoidal is very rarely that will be used. That's why we can that is not that much a required thing basically. Now we'll see the time response of a first order control system. This is very important. Time response of a first order control system. Time response of a first order control system. So for this, let us consider first order system, how it look like in a in terms of its block diagram. So let us consider the following. Let us consider the following first order control system with negative feedback. So the first order control system is look like this. Because it is a unit feedback, that's why your h of s equal to 1 here. This is your g of s, this is your h of s. Normally, actually in this loop you have g of h of s, but for unit feedback h of s is 1. If you put minus, that is called negative feedback here, and obviously this is what your r of s input, always it is plus only, it is your c of s. So this is what the representation of the first order system. The first order systems looks like this only. This is here your error signal E of s. Error signal E of s is nothing but the output of this summing point. So this is what the basic diagram of a first order system, and I will explain you later what is a order of a system. What is a order of a system? Okay, normally. So right now, for the sake of understanding, remember that normally the order of a system can be identified for any given control system. The order we are talking about the first order. Okay, so what is order actually? How the order can be identified? how the order of the system can be identified. So for any given control system, the order of the control system can be identified, can be expressed from the definition of the transfer function itself. First of all, you have to find out the transfer function of the system. So your transfer function is nothing but it is the ratio of some numerator by some denominator. And in this case, your transfer function is nothing but C of S by R of S, obviously. So C of S by R of S is equal to transfer function. From this transfer function, the order can be identified. The order can be expressed. That I will tell you in little bit in next presentation. So right now you see this is the a basic block diagram that can be represented for a first order control system. Now you just find out the transfer function of this system. See, you know g of s value, this is what your g of s, this is what your h of s, it is a unit magnitude, nothing but unity feedback, nothing but your h of s value is what here, only straight line, nothing is given here, means in this case consider your h of s feedback element as 1. Therefore find out c of s by r of s for this negative feedback. In the very beginning presentation we have seen this basic definition of this particular, how to find out the transfer function. So here if you apply our negative feedback loop, then c of s by r of s becomes c of s by r of s is equal to, what is the actual formula? It is g of s by 1 plus g of s into h of s in general for a negative feedback. This is the definition, no, for negative feedback. What is g of s? It is 1 by t into s. This is what your g of s, 1 by, then whole by 1 plus, I am substituting these values in this formula, 1 plus just 1 I have mentioned, g of s is nothing but again your 1 by t into s into h of s. H of s is nothing but 1. Okay, then remove this diagram and little bit simplify that. What will be the so this equal to c of s by r of s is equal to, if you simplify this, obviously it is 1 by t into s by, it is 1 plus 1 by ts into 1, nothing but 1 by ts only. This implies, and take cross multiplication here, 1 plus 1 by ts means your ts is multiplied with 1, ts will come, and in numerator 1 by ts will be there itself. Denominator, it is 1 into ts multiply, means s, t into s will come there, plus 1, is it not, by t into s. Then obviously this ts will be cancelled out. Then what we will have, 1 by 1 plus t into s, is it not? That is what your transfer function. Therefore your transfer function is equal to c of s by r of s is equal to what, 1 by 1 plus t into s. This is what your transfer function. This is what the transfer function of your first order control system with negative feedback. Remember that the order of the system can be defined for both open loop system as well as closed loop system also. The order of the system can be expressed for both open loop as well as closed loop. So as far as your first order control system is concerned, this is what the transfer function. Transfer function is equal to c of s by r of s by 1 plus t into s, where t is called as the time constant of the system, which is very important parameter. In a later subsequent presentations you will definitely understood what is time constant. Okay, right now for the understanding, you just note down this one. So C of s by R of s is equal to 1 by 1 plus t into s. So all this is in terms of the Laplace transformation only. That's why you will have the parameter s, because it is in the form of Laplace transformation only. Now from this you write the expression for your output. C of s is equal to what? So C of s by R of s is equal to this. From this you write the expression for C of s. What is our next equation? What we will get? So from this I will write the expression for C of s. So C of s is equal to what we will get? It is 1 by 1 plus t into s into my R of s. Is it not? So just I want to have the expression for C of s. C of s is equal to, take this denominator portion R of s to the next right side, then obviously it goes into multiplication. Therefore 1 by 1 plus t of s into R of s. Okay, now this is what your output, this is what your output basically. This is what your output in terms of Laplace transformation. Now, what is our target actually? To find out the time response. Time response. What is response? Response is the output. What is the output? C of s is the output. So, C of s is the output. This is what our actual output. This is what our actual. But I want to study time response, output, or otherwise you can call it as response. Is it not? Output or response. But what I need, I want time response, not simply response. I want time response. What is the meaning of it? Time response is nothing but I must want C of t, not C of s. I want C of t. Means what is C of s actually? C of s is nothing but the Laplace transformation of C of t. Is it not? C of s is nothing but Laplace transformation of C of t. Actually, in the previous presentation we have seen, actual input is R of t. For any given control system, your R of t is input, C of t is output. So for the C of t, we have applied the Laplace transformation. That's why we have C of s. Now we obtained the expression for C of s, from which I want again back the C of t. Then what I should do? Here I have to apply the inverse Laplace transformation. The inverse Laplace transformation to this C of s. So if you apply, R of t and then C of t, clear? So if you apply the Laplace transformation to the input R of t, you will get R of s. So if you apply Laplace transformation to the R of t, you will get R of s. Similarly, if you apply Laplace transformation to the C of t, you get C of s. Now you have expression in R of s and then C of s. Now from this C of s, if I want to C of t back, then you have to apply inverse Laplace transformation to R of s or C of s, whatever it is. So here we have applied a Laplace transformation. Because of this, we have obtained R of s. Now from R of s, if I want to get this value R of t or otherwise C of t, then for these values you need to apply inverse Laplace transformation. Then you will get C of t. Right? Then what I should do now for this expression? I have to apply inverse Laplace transformation. So by applying what? By applying inverse Laplace transformation. By applying inverse Laplace transformation to this expression, then that means LT inverse is C of s. This is equal to LT inverse, means inverse nothing but LT nothing but Laplace transformation. It is inverse. That's why it is called inverse Laplace transformation of C of s. And similarly, LT inverse of 1 by 1 plus t into s, and you can write R of s also here, no problem. Combinedly, I can write combinedly, no problem. You can write individually or you can combine here also, nothing wrong in that. So LT inverse of total. Then this implies, so upon application of inverse Laplace transformation, you will get C of t itself. Directly you can write. Upon application of inverse Laplace transformation, you will get C of t. C of s can be converted into C of t if you apply inverse Laplace transformation. Then here what we should do? So this is what basically. Okay. So this is what your inverse Laplace transformation of, or otherwise you can write this also, R of s or inverse Laplace transformation of 1 by 1 plus t into s. Like that also you can write. A little bit expansion, nothing wrong in that, for more clarity. This is what in general C of t is equal to LT inverse Laplace transformation of input R of s, and then this one we have. Now we have to apply our conditions. So this is what your final expression for this first order control system. Now I must consider what is the input for this my first order control system. So far we have seen the block diagram and we have just obtained the equation for C of s or C of t, that's all. But we have not discussed about what type of input we have applied to this control system, first order control system. Now, so apply, let us assume that your input is a unit step signal. Let us assume that your input is a unit step signal. Okay. Now let us see. Likewise, so this equation is the standard equation. Whatever we have derived now is the standard equation, and so C of t or C of s in terms of your input and then gain. So now your R of s, you must apply the value of R of s. Is it unit step signal, or is it ramp signal or parabolic signal or impulse signal? Based on the given input signal, you have to mention in that. Therefore, what we have, what is our final? So it is nothing but C of t is equal to, normally it is R of s into 1 by 1 plus s in, t into s. Is it not? Basically, this is what we have now. So for this, let us consider our input as, let us consider R of t is equal to unit step, because this is the very beginning, very basic building block, you can say. Okay, step input signal. So R of t is equal to unit step signal. Consider your input as R of t as unit step signal. Then if R of t is unit step signal, what is your R of s? R of s equal to, what is the R of s? We have seen in the previous presentations. R of s is equal to 1 by s, because R of t is equal to 1, unit step signal. Then R of t is equal to 1. Then if you apply the Laplace transformation for the R of t, your Laplace transformation of R of t is equal to Laplace transformation of 1, that is nothing but 1 by s. So substitute this R of s value in this expression, then you definitely will have this 1 by s into 1 by 1 plus t into s. This is what your expression, no? This is what your C of t is equal to, like this. Okay, so 1 by s into 1 plus t into s you have. This is what your expression basically. And again, what I will do here, I will do a small thing here. So here in 1 plus ts, take t as common. Take t as common. What we will get? Because just I want to bring one important relation here. This implies C of t is equal to, so it is 1 by s actually. Take in this parameter or in this thing, take t as common. If you take t as common, what we will have? S plus 1 by t. Shall I write like this? If you take t as common outside, then s will be there and t will comes 1 by t form. T will become here. So already this. And furtherly, this I can write, and subsequently I can write this. This 1 by t is there, no? I will write in numerator part 1 by t, and from here s into s plus 1 by t. Clear? Can I write like this? This 1 by t is there, no? This t I have just written in numerator part like 1 by t. No problem. You can write like this. Then by s will be there in denominator, s plus 1 by t. Now you use your partial fraction method. You use your partial fraction method. You already know that. As per the partial fraction, you can write this denominator part. This can be written as a by s, clear, plus b by s plus 1 by t. Okay, a by s plus b by s plus t. Is it not? So all this is you can use in Laplace transformation formula only, no problem. C of s, let it be in C of s only. After that we will change inverse Laplace transformation form. Finally, we apply the inverse Laplace transformation. You can put in C of s form only. Now, so from this partial fraction, we have to find out the value of a and b. A and b. So how? So in order to get the value of a, this C of s value nothing but this one. This is what your C of s, and finally for this C of s we are okay, representing in partial fraction method. So obviously your C of s is this one. So in order to get your a value, so you multiply this s of s with s and put s value as 0. Then you will get the value of a. Very simple. So in order to get the value of a, you just multiply the C of s with s, substitute s value as 0. Okay, s value as 0. Because normally s plus a form will be there, s plus some form will be there. So it is directly only s, therefore s plus something is not there. Normally some value must be there. If nothing is there, s value should be applied as 0. And okay, similarly, if you want to find out the b value, what we should do? You just multiply again your C of s with this same number, substitute s value is equal to minus 1 by t. Clear? So substitute s is equal to minus 1 by t. There you will get the value of b. Now, first of all, I want to find out the a value. So to find out the a value, so this C of s is nothing but this. This everything is multiplied by s first and substitute s equal to 0. Very simple. So what I will do here, just I will erase here. So I will erase this also. So from this, multiply this everything with s, nothing but this implies in order, so a value is equal to s is multiplied by this one, nothing but s into 1 by t, is it not, by s into s plus 1 by t. That is the meaning of it actually. Clear? This is what C of s. For this total factor C of s, I am multiplying with s. Means s comes here actually. That's what. S into everything. And here you substitute in this s equal to 0. This implies what you will get. So if so, this s will be cancelled out, and substitute s value with 0 here. Then what is that? 1 by t will be there in numerator. By, if you substitute s value 0 here, it is 0 plus 1 by t. Therefore 0 plus 1 by t is nothing but 1 by t itself. Means it is 1 by t by 1 by t. Both will be cancelled out. Your value is 1. Therefore what is your a value? A is equal to 1. Clear? A is equal to 1. Therefore you can write here. Therefore a is equal to 1. A is equal to 1. Similarly, find out the value of b. So for this b, what we should do? What we should do for b value? Again, multiply this factor, this entire c of s with this one, and substitute s equal to minus 1 by t in that, and you will get b value. So for that, what you will do? A value is 1 already we obtained. Now go for the b value to find out the b value. So for that, b value is equal to, so s plus 1 by t is into 1 by t means this one by, it is s into s plus 1 by t. This is what, no? And in which you have to substitute s equal to minus 1 by t. In which substitute s equal to minus 1 by t. Likewise, this implies what you will get? It is s plus 1t, s plus 1t, both will be cancelled out. Clear? Then s value is minus 1 by t, you substitute. S value is minus 1 by t. It is 1 by t, and then s value is minus 1 by t of, that's all, because both are cancelled out now. It is 1 by t and it is minus 1 by t basically. So means both are same. It is 1 by t, it is 1 by t, it is minus 1. Therefore, what is your b value? What is your b value now? Therefore, b is equal to minus 1. Therefore, a value is 1, b value is minus 1. Now substitute these two values in earlier expression. Substitute these two values in our previous expression. That is what? C of s is equal to, what is that expression actually? What is that expression? It is 1 by t by s into, okay, it is s into s plus t. So we have taken, clear, s into what we have seen that. So as you have seen that 1 by t, s plus 1 by t, clear, this is equal to what we have seen. It is actually a by s plus b by s plus 1 t. That's all. And now this is equal to, substitute a value is 1, it is a by s, I mean 1 by s, and here it is minus 1 by s plus 1 by t. Clear? 1 by s and minus 1 by s plus 1 t. This is what your c of s basically. And now for this, substitute from this, now you apply inverse Laplace transformation. So apply inverse Laplace transformation. So we know that the Laplace transformation of c of t is equal to c of s, and inverse Laplace transformation of c of s equal to c of t. Means inverse only, means you will get c of t directly here. This is what c of t you will get here. This is equal to LT inverse of 1 by s minus LT inverse of 1 by s plus 1 by t. So this is equal to 1 by s. 1 by s. What is the inverse Laplace transformation of 1 by s? What is the inverse Laplace transformation of 1 by s? So in the very beginning we have seen your input step r of t is equal to 1. If r of t is equal to step input, that is 1. If you take Laplace transformation of r of t, nothing but your r of s, nothing but Laplace transformation of 1, nothing but your 1 by s. Means Laplace transformation of 1 is 1 by s. If you apply inverse Laplace transformation to this, obviously that value is 1 only. Clear? So LT inverse of 1 by s is equal to, if you apply inverse Laplace transformation, you will get 1. You will get 1. Therefore, here LT inverse of 1 by s is nothing but 1 only. It is 1 minus. What is this actually? What is this actually? There is another important property of Laplace transformation. There is one important property of Laplace transformation. Laplace transformation of e power a into t. Laplace transformation of e power a t is equal to 1 by s minus a. This is one property. Similarly, Laplace transformation of e power minus a t. If it is minus a t, then it comes 1 by s plus a. If it is plus, then after the transformation, s minus a will come. If it is minus, then it comes s plus a. This can be derived from the definition of the Laplace transformation itself. You can try, or otherwise I will explain you in later, presentation also. These are the very important definition. L of t of e power a t is equal to this. Now, if you see here, LT inverse of s plus 1 by t, nothing but s plus a form. Let us you call it as something a. S plus a form. It is there in s plus a form. Okay, s plus a. S plus a is nothing but this form. It is there in s plus a. 1 by t as a. Means it is 1 by s plus a. 1 by s plus a. Means that if you apply inverse Laplace transformation, obviously you will get this e power minus a t form. Your a is nothing but 1 by t here. Then obviously if you apply that, we will get e power minus a is nothing but 1 by capital T. This everything is a, and then small t will be there. That is what your C of t. Clear? Clear? Okay. So it is LT inverse of 1 by s plus a form. S plus a. 1 by t considered as a. S plus a. 1 by s plus a. This is what? 1 by s plus a. Now, apply inverse Laplace transformation to this. If you apply inverse Laplace transformation to this, you will get e power minus a t. That's what in time domain. E power minus a t. Minus is there. A is nothing but 1 by t. Into time small t, you will write to small t. You have to write there. And now, your C of t is equal to, from this implies your C of t is equal to 1 minus, in simple I can write e power minus small t by capital T. Small t by capital T. This is the expression for your time response. If the input R of t is a unit step signal, if your input is a unit step signal, then the corresponding output or response of a first order system is like this. Now, here you can see that. Here you can see that for different values. Let us see, for example, here t value, you can write t value is substitute 0. T value small t is nothing but you can write 1t, because small t by t is there. This capital T is nothing but time constant, and your t must be in terms of t's only, 1t, 2t, like that, and again 1t, 2t. small t is equal to some 3t, t is equal to some 4t, t is equal to some 5t. You can go up to t value is equal to infinity also. You can go up to, starts from 0, go to infinite. Then what? For all these values of t, what is your response? Means correspondingly for t equal to 0, your C0 is equal to, it is 1 minus e power minus 0 by t. This is equal to 1 minus 0 by something 0, e power 0 is 1, therefore 1 minus 1 is 0. So for t equal to 0, okay, for t equal to 0, this entire becomes 0, e power 0 is 1, 1 minus 1 it is 0. Your response C of 0 value is 0. Then 1t, then for t is equal to 1 actually, okay, or 1t you can write, no problem. C of 1t is equal to, it is 1 minus e power minus small t is nothing but 1 into t by capital T is equal to tt will cancels out. This is 1 minus e power minus 1. What is the value? Similarly, here C of 2t, this is equal to 1 minus e power minus t nothing but 2t, 2t by t, and these two will be cancelled out. It is 1 minus e power minus 2. What is the value? Similarly, for this, if you substitute from your calculator e power minus value, you will get definitely, you will get, it is for 1t, you will get some 0.632. And for second e power minus 2t, you may get 0.865 like that you will get. Okay, and similarly for 3t, c is equal to 3t, this is equal to 1 minus e power minus 3t by t, this is 1 minus e power minus 3 value, that is 0.9, you will get 95 like that. You observe that. So from 0 to, as your time goes to increasing, your value here also going to increasing basically 0 to, and where t is equal to infinite, finally if you see t is equal to infinity, means some c is equal to, for infinity what you will have, it is 1 minus e power minus infinity by capital T. So infinity by something is infinity, e power minus infinity is 0, that means 1 minus 0 is equal to 1 you will have. Means you observe carefully, for t equal to 0, your value response is also 0, it is little bit going, increasing 6.6, 0.8, 0.9, and it is up to the maximum value is 1. We have already reached plus infinity value here. In time domain, we started at 0, we have reached infinite, and at infinite value of time, your output is 1. Therefore, if you draw this information, everything in graphical representation, you will understand what is a transient response, what is a steady state response. I will show you. Okay, so this I will erase. And now graphically, you can show like this. For unit step signal, this is what your C of t now, because already we have brought one expression for that. It is time actually. It is 0, is it not? This is, you can say 1t, 2t, 3t, 4t, 5t, up to so on and so forth, up to it is going up to plus infinite, up to plus infinite. And if you, and again here t value is going up to infinity also. For infinity, what is C of t maximum value? 1. The maximum value is 1. Therefore, your magnitude is 1. So, you can draw a dotted line there. Likewise, and 0, the maximum value at t is equal to infinity, the output value is 1 only, maximum is 1 only. Then the 50% of that somewhere here, 0.5, maybe here in between basically. Now for 1t, for 1t, what is that? For this 1t, t is equal to, as per that expression, if you substitute t value as 1t, then it is somewhere 0.632. 0.632 is nothing but somewhere above 0.5, maybe here. For 2t, what is that? It is 0.865. little bit above somewhere here. At 3t, it is something 95, somewhere above this value. Clear? And 4t, what is 4t? 98, something 98 it will come, 4t, somewhere here. And for 5t, almost all it reaches to 99 also. It comes to 99, like that. And almost all as t tends to infinity, you will get one value. You will reach the maximum value at infinity, you can say. If you add all these points, no, you will get like this. Just try to combine all these points and try to draw one line here, straight line, it will come like this. Okay, let us say join on this point itself. These are the different values. So the graph will be like this. This is your response. This is what your response, time response for step input, signal. Now, if you see from this graph, actually it is starting from 0, and as our input is depending on time, so it is varying. As our time is changing, it is also going to change up to certain point. Almost all, you can say up to 40, or you can take up to 50 also. From here you have steady state value, constant. Whatever the value you apply, it is almost all merged with this line, already touched to 1, and it will not go beyond that, and it will be constant. Means that what we can say. So this is what, in which I can show you that up to this portion, before this portion, the graph which is available in this area from 0 to maybe up to 5t area, 5t, or you can take up to 5t. So this graph is called as this response is called as transient response. This is called your transient response. This is what transient response, which is I already told you in the 23rd lecture. And now this response is called as steady state response. This is called steady state response. This is called as t tends to infinite, from where you will have the constant value, whereas up to this point it is going something like this, one curve shape. So this is called a transient response. This response is called steady state response. Therefore the overall, the sum of time transient response, steady state response, combinedly the total, this is called as the time response of a first order control system with the input, step input. And we can derive for ramp input also. If the input is unit ramp, what could be the output? If the unit is unit parabolic, what could be the response? We can. So this is what the response of first order system, and in subsequent we will see the rest part of the also. So with this, I would like to close in today's presentation. I hope that you understood very well, and definitely request you all, if you want to like it, you definitely can subscribe to this channel. And also I request you once again to not forget to forward these presentations, these lectures to your friends who are really needy to understand the subject. And definitely I wish you all good luck, and in I expect you to become more expert in understanding these subject concepts. Thereby you will excel in your career. Thank you one and all.